Happy day, students. Let's continue with where we left the class yesterday. In the yesterday's class, we were talking about conservation of angular momentum. Okay, what is conservation of angular momentum? We saw if there is no external force, now the no external torque, if the torque is zero about any axis of rotation, then we can say that about that particular axis, angular momentum is conserved. Okay, and we did plenty of questions on that, and after that we did some collision questions also, right? But there is one question that I wanted to discuss with you, which is on the conservation of angular momentum. Suppose I have a disk. Okay, there is a disk over here, so radius is r, and suppose at this point this cross is there, and at this cross there is one girl standing. There is a girl standing, right? Standing, it's at rest. Now, all of a sudden, girl started moving, right? Girl started moving along the circumference, along the periphery of this one. So the question is, after what time she will be back on this cross? Okay, she will be back on this cross. What is the question? The question is, if girl starts moving along the circumference of the disk, where will she be back? On the same spot from where she started the journey. Okay, find the time when she will be at the cross. This cross means is what? From where she started the journey. Okay, when she will be back, she will be at the cross again. Starting point. Okay. So what do you say? When she will be back at the cross, does she has to travel 2 pi? Then she will be back over here at the cross again? No. Why? Because if the girl is moving like this, that means our disk will be moving in opposite direction. Okay? Girl is going to move in this way, like this. Now how she will move? She will push the disk back, obviously. So disk is going to move in opposite direction. Okay, now suppose that the girl, when reached here at this point, this cross came to this point. And this is what we are searching actually. Okay, so this is the point. And at this point, if I say the girl has moved by theta, then by what amount disk has moved? Disk has moved by this angle. How much is this? This is 2 pi minus. Isn't it very similar to the question that we did in conservation of momentum? One boy is moving on the plank. Okay, when the boy is at the other end, how much is the plank moved on the left direction? Remember that? Exactly similar question, right? There what we did, initial momentum 0, final momentum of the boy plus momentum of the plank. Exactly same thing here also. Initial angular momentum in this case also is 1, because initially nobody was moving. So initial angular momentum is what? 0. Right. Final angular momentum. Now, first of all, about what we are taking angular momentum? About the center, about the disk. Right? Because we know that about this torque is 0. How? On this girl, who is acting forward? Friction. Because of friction, it's moving forward. And on the disk, where is friction? So total torque along the axis is what? 0. Right? So we are conserving angular momentum about the center. So final angular momentum is what? I will write that angular momentum of girl plus angular momentum of disk. Very, very simple. Right? Now, what is angular momentum of the girl? What you can say? What kind of motion it is doing? Okay, you can say that it is doing circular motion, you can say it that way also. I omega also we can write, or MBR also we can write. That is our wish. Okay, so I am going with I omega. So it's moving in this direction. So in which direction it is coming? It's anti-clockwise. So angular momentum is outside. Let's take that as positive. Okay. So what it is, if its mass I say is m. Okay, and mass of the disk is smaller. So we can say that there is mr square. And omega means what? Average omega means what? The total angular displacement by time. Right? So theta by 2. Right? Then this again I omega only obviously. So mr square by 2. Again it's omega. Its omega means 2 pi minus theta by 2. Equal to 0 because we are going to equate both. So 0. Bring it this side. So mr square by 2. 2 pi minus theta by t equal to mr square into theta by t. This t and this t gets cancelled. This r square and r square gets cancelled. Okay, now if the masses are given clearly, suppose this girl's mass is given, suppose 40 kg, 50 kg, something like that, or the relation is given. Let's say that this mass is 1/4 of the mass of the girl, or anything like that. Okay, let's say that. Okay, m is m by 2. Right? Why I am saying this? Because then value will come. Okay, so what we have, m is m by 2, and this is already m by 2. So this is m by 4, 2 pi minus theta equal to m theta. This is cancelled. So what we got here, 2 pi minus theta equal to 4 theta. Right, so 2 pi equal to 5 theta. So theta equal to 2 pi by 5. Theta equal to 2 pi by 5. So after 2 pi by 5, 2 pi by 5 actually is how much? 360 by 5. That is 72 degrees. So girl will move 72 degrees. Okay, and the disk will move 360 minus 72 degrees. So here they are going to position you got. Right? Position we got. Now what more we have to do? So 72 degrees in how much time? So theta equal to omega t we can bring on an average. So t will be getting as theta by 1. Normally t is not asked. What we have asked already. When? Where? Okay? Make it where. Okay? Normally it will be asked as where. And if suppose when is asked, then omega will be given. Okay? Omega will be given to us. I hope this is clear to you. Okay? This was one of the things that I forgot to tell you yesterday. So note this one first, then we'll move ahead. Right? Okay guys. Let's see the next one now. Okay, yesterday we were talking about collision also, collision with the rod. And we did questions based on, right? Now, similarly, I asked you one more question. A random question, okay? It's not that it's related to anything. You have to identify how to do that. And it's a practical thing basically. And what it is suppose that there is a swing, okay? There is a swing. And this is how the swing is. And here a person is there sitting, okay? Sitting. Right? And he's swinging. He's swinging the omega. Right? Now he thought of increasing his speed. He wants to go with more higher, he wants to increase his speed. Okay, but he cannot touch the ground. He is slightly above the ground. So he cannot touch his feet with the ground and push himself. Right? So somebody here told him that when it is reaching here, stand up. Okay, stand up on the swing. So what he did is, he did something like this. He stood up. He's holding it and he stood up. Okay, then immediately omega 1 changed, or rather omega changed. What has happened? Has omega increased or omega decreased? We have to give the answer. What will happen? Omega is going to increase. Omega is increasing. Omega 1 is more than omega. How can we see? Now look at this position right now. Okay, what is the force acting on this one? It's on the mg. Okay, let's talk about torque of mg at this point, about this axis. What is the torque of mg? 0. Here also 0. So at this position where it is in vertical, can I conserve angular momentum? Yes. So I conserve angular momentum here and in this position. Right? Fine, that's okay. Now if suppose that here is omega, that's speed, and here moment of inertia is I1, and here moment of inertia is I2. Now you can ask me that why it is different, same volume, same mass. The reason for this is, at this position, the boy's center of mass is here. So moment of inertia will be m into this distance as well. But when he's standing, his center of mass is here. Okay, it's at center. So what? This is now, this m into this distance square is different. So because of that, I1 and I2 are different. Okay, which one is more? This is more. Because this is farther. This is far. Who's far? Mass. Position of the mass is far as compared to this one. So I can say that I1 actually is more than I2. I1 is more than I2. Right? Now if I conserve angular momentum, I1 omega 1 equal to I2 omega 2. See what's happening there. I1 omega equal to I2. Make it as omega 2. Right? I2 omega 2. Now then, I1 by I2 equal to omega 2 by omega. Now you already did that. I1 is greater than I2. So that means I1 by I2 will be greater than 1. I1 by I2 is greater than 1. So that means this is greater than. So that means omega 2 is more greater than omega. So your omega is increased. You become faster. So if you become faster, what will happen? You will travel more. Your kinetic energy is increased. Omega is increased means what? Your kinetic energy is increased. Why? Half I omega square it is. Yesterday we saw that when a girl is rotating and she folds her arms, then what happens? Omega was increasing. And if omega was increasing, I told you that the kinetic energy is increasing. And then I asked you also, why? Because of internal forces, internal energy. The same here also. It's not that easy for him to stand up. Okay, he has to work. And that one is going into increasing kinetic energy. Okay? So that's all. This is what we had to discuss as far as conservation of angular momentum is concerned. Now, let us talk about angular impulse. Angular impulse. Do you remember impulse we studied in last chapter? Conservation of momentum, collision. Okay, what it was, do you remember that? When very large force acts for fraction of seconds on any particle. When very large force acts on any object for fraction of seconds, then that is called impulse. What it will be here? Angular impulse. When very large torque may be constant, may not be constant, acts on an object for fraction of seconds. Okay, then it's called what? What it generates? Angular impulse. Okay? So, angular impulse. What is angular impulse then? When very large torque acts for fraction of seconds on an object that is called If you remember, linear impulse we represent with J. Okay, and what we got? What was J actually? First I am writing about J, okay? F dt. So it's F dt, right? So vector component. Now F dt was what? Why F dt? Because it was acting for a fraction of seconds. But was this force variable or constant? Anything is possible. But since it was acting for such a small duration of time, we cannot determine whether it's a constant force, variable force or not. Then how to measure it? How to measure it? If you remember that this F dt we return as, what we return as? We said that F basically is dp by dt. Right? So from here we return F dt is basically dt. Right? This is what we said. Now since you are integrating it for time t, that means you are finding what? Average force. Because maybe variable, maybe constant, let it be whatever it is. So F average into delta t was equal to what? Delta. So the value of impulse we used to calculate with change in momentum, because this we can see. But measuring this force, how much force is acting, was difficult. So we used to calculate with change in momentum. Exactly same thing we are going to do over here. Okay, now what is this angular impulse? The angular impulse we are writing as, what do we have written? Torque. So it's basically torque dt. Torque dt. Okay, this we are calling as angular impulse. Or you can say this one relation between angular impulse and linear impulse is what? Linear impulse J. So R cross J, I can say is angular impulse. Okay, same like R cross P is L, R cross F is torque. Same way R cross J is angular impulse. Okay. Let's suppose I give you an example, and in fact we'll do a question also on this one. If suppose this end I say is hinged, okay? This is a rod, mass and length, and here apply an impulse J. So if I have to find angular impulse, then I will say that angular impulse is basically what? L cross J is angular impulse. Okay, that's what I have to tell you here. R cross J means basically what? L cross J. Which direction is that? What is the direction? Towards you. Okay? Towards you. Okay, so let's come back over here. So angular impulse, we have written torque dt. Right? So torque dt basically is what? We have also studied about torque. What we have studied about torque, we said that torque basically is dl by dt. You know this. And since we are talking about impulse, then we can write this as torque dt. That's what the impulse is basically. And that's equal to what? Change in angular momentum. Right? Suppose we are talking about average torque, then average torque into delta t will be equal to what? Delta n. Same relation what we got for impulse, same is coming in angular impulse. Not same, similar result is coming in angular impulse also. Okay, so this is what we have the meaning of angular impulse. We will do the problems on this one, we will understand in a better way. Okay, so this is clear, I guess. Okay, units, what are the units of this one? Same unit as angular momentum. Okay, nothing else, because this is equal to change in angular momentum. So what was angular momentum's unit? What was angular momentum's unit? Kg meter square per second. Okay, because angular momentum is what? I omega. I is what? Kg meter square. And omega is radian per second. Radian is not considered, so per second. Or you can say MVR kg meter per second into meter, kg meter square per second. So unit is kg meter square per second. Or suppose you want to write in terms of Newton, then this is Newton meter and this is second. Right? So Newton second meter, Newton meter second, whichever is convenient to you, you can use. Okay. Alright. Let's see how the question will be there. As I told you already, this is basically a cross product of R and impulse. And impulse is what we have studied already. So let's take the question, the same question that actually I told you a little while ago as an example. Let's take that only. Okay, so this is rod here, mass and length, and here this is hinged. Right? From here, given impulse. Question asking, find angular velocity of the rod. Find angular velocity of the rod. Simple question. Before that, before applying the impulse, was rod at rest or it's moving? It was at rest. Right. Now, after applying the impulse, what is happening? It's moving. How it is basically? Something like this. If suppose this is a rod, okay, and I am holding it like this, and this is at rest, okay. From here, from this place, if I apply impulse like this, what will happen? Has it moved? Yeah. See? So, what angular velocity I have to find? That's what we are finding. Easy that is, simple calculation. But in this one, first of all, angular impulse that we are writing, what is that? Let's say that is actually L cross G. Which direction? Towards you, right? Say L cross G. Now L cross G is angular momentum. Or you can take it in terms of tau dt. That way also we can. Okay, this is fine. One form. Tau dt also you can do it. Now tau dt basically what? This J. This J is what actually? This is FDT. So I am going to put it over here. J is FDT and this L is basically L. Sorry. J is FDT. Right. Now L cross F. That's R cross F. R cross F is what? Tau. So this becomes tau. Okay. Fine. Now this L cross J is actually equal to what? Change in angular momentum. So L cross J is J into L. L into J I am writing directly because angle is 90 degree and direction will be I don't know. Equal to what? Change in angular momentum. That means L final minus L initial. Okay. L initial is 0. L final, I will write it as I omega minus C. So L into J. This L is actually length, okay. Better is to make it as small because then you will not be confused with the angular momentum that we are using, okay. L into J. That's equal to I omega. What is I? ml square by 3 into omega. So this L and this L gets cancelled. We got omega value. What is omega value? Omega value is 3J by ml. Right? That's it over. If they give it certain value, we'll use that value. Right? Let's see another one. Another question we'll do. Okay. How's the other question? Okay. Same problem. See, you can take anything other than rod also. We know what is here. Rod basically means this moment of inertia easily calculated. You can take anything that you want, right? So it's here. This is the rod. Here it's hinged. let's say this is L by 4. Okay, and here impulse I am giving. In impulse I am giving with an angle. Okay, J is acting like this. And this angle you can say 77 degrees. Right? Mass of this one is M. Question is saying, what will be the angular velocity? Okay. Find angular velocity of the rod after impulse. Angular velocity of rod after impulse. Right? Is it okay? Now we can see that this impulse basically is applied inclined way. So we know that it has got two components. This here is j cos 37. J cos 37 means 4j by 5. And another one is this 3j by 5. My question is this 3j by 5 can produce any angular impulse about this axis? Answer is no. No. Because R, this is R, and J, they are anti-parallel. So they cannot produce any angular impulse. This only can produce angular impulse, yes. And this distance is what? 3L by 4. So what here will be writing? Impulse into perpendicular distance from axis of rotation. Okay. So 4j by 5. Directly I am going, okay, into 3L by 4. J into L, which is actually impulse tau dt. Okay, equal to what? I omega. Now what is I about this? If you remember yesterday we calculated this. About this L square by 12. Then M L by 4 whole square. It became 7 M L square by 48. This is I. Omega final minus omega initial. Now, omega initial is what? It was at rest. So here anything, yeah. So 3 by 5 JL equal to 7 ml square by 48 into omega final. L and L gets cancelled. That's all. So our answer is 48 into 3. 48 into 3 J by 35 ml will be omega. Right? So in inclined way, the question is coming like this, we can do. Okay, that's fine. Another one we take in which, let's say this rod is having initial angular velocity. Okay. Then how to do it? Let's see. Okay. So here rod only I am taking. Let's assume this rod is already moving with omega or omega naught above its end. Okay. And its mass is m, length is l. You give impulse in this direction, that is j, and we want to find final angular velocity. Now this impulse, even it is possible that something is coming and colliding with it. Okay, that also we can call as impulse, but that way we have already solved the collision questions. Okay, without taking angular impulse. But if suppose you want to take, you can. Right? Okay, so then this j is coming and hitting it. So what we want again, final angular velocity we want. So let's write again j into L, that is the angular impulse, equal to what? Now j into L is in which direction? It's towards you. And in which direction is rotating? Opposite direction. So if I am going to write change in angular momentum over here, LF minus L initial. Now you can see it's in opposite direction to the direction in which already rotated. So either I need to write this is negative or I will be writing this is negative. Our wish. So I am considering that outside itself is positive. So this is negative. Okay, so J into L minus I same ml square by 3 is omega final minus omega initial. That's omega out. Okay, omega final we are calculating this L and this L is common. This is coming as minus 3J by ml equal to omega final minus omega initial. So what is omega final? Omega final is omega naught minus 3J by ml. Because we know that omega will be decreasing because it's supplying the impulse in opposite direction. Right? So these kinds of questions are there, simple questions are there, right? Let's see then few more questions we do on angular impulse. Okay. See then, if suppose I take two discs, okay, this is this one, it's rotating with angular velocity omega 1 or omega, its radius is r. Okay, another disc is there. This is another disc. Okay, and its radius is r, and this is at rest. Okay, its moment of inertia and its moment of inertia are different. You can see the size is also a bit different, but this is at rest and this is actually moving. And there are actually in this one, there are gears like this. Okay, it's like this. I hope you have seen this kind of a disc. Where you get this kind of a disc? If suppose you are going for sugarcane juice, okay, on the roadside, you can find that these are actually called gears. Okay, this kind of disc are there. Here also there are grooves in that, like this. Okay, but this is at rest, this is moving. Now what we are going to do? We are going to bring them in contact. Then when you are bringing them in contact, what happens? Finally, they will start moving together. This will also get the motion. Right? This will also get the motion over here. Is that okay? Question is, what is the question? Question is, find the angular velocity finally for both. Okay? Or find the relation between angular velocity of both. Something like that the question is. Even I have to frame the question, but we'll see that. Okay? Let's start doing. We'll come to know about the question. Okay? And this are brought in contact with each other. Right? What is happening? How to proceed about this question? Now see then, if I can make this disc, the bigger disc like this, the bigger disc, and this is the smaller disc. Okay? This is rotating. This is rotating like this. You brought this in contact. So in which direction this is going to move? How? Because this groove here will fix into this groove. But since this groove is going up, this will also start going upwards. Right? So that means on this groove here, force is being applied in this direction. Right? Which force it is? Contact force, obviously. Friction also you can call. Suppose I would not have given you grooves. Without grooves, it's the same question you are solving. Then you could have said that this is friction. Okay, it's a contact force. So contact force of this disc on this disc is in this direction. So because of this disc on this disc, reaction, this direction. Yeah. Right? Fine. So now the question is, can I conserve angular momentum of the two discs and solve it? Okay, before that, finally, when we know that this will also start rotating now, if this is going upwards, then this will start rotating like this. Right? And we also know that this force, or rather this force is actually trying to decrease its speed and this force is trying to increase its speed, then only they will be coming to the same kind of motion. Otherwise, what will happen? The gears will keep on braking. You'll get the sound. Do we get the sound when we go to sugarcane juice shop? No. It will work properly. Okay. So that means there is no slipping is happening. Hardly any slipping. So here also there will be no slipping. And when no slipping happens, when the two bodies which are in contact have the same speed. When the two bodies which are in contact have what? Same speed. Okay. So this point is also going up, this point is also going up. Let's assume that its angular velocity now has become omega 1 and this is omega 2. So this is speed here, this point speed here will be what? This radius we have taken r1. So this will be r1 omega 1 and this will be r2 omega 2. Yes or no? Right? So r1 omega 1 equal to r2 omega 2. This is our first equation. Right? But here two unknowns are there, no? Omega 1 is also unknown, omega 2 is also unknown. So if suppose omega 1 and omega 2 we are calculating, at least we require two equations. One equation I have, one more equation is required. So for that equation, shall I conserve angular momentum? That's what I was asking. Suppose force is F here, force is F over here. So its torque about this point. Where? Upwards. So it's towards you. For this one, inside. So total torque we can say is 0 about this one. Can we say it or not? Because of these two forces, yes I can say. But there is one more force. Which force? Hinge of this one. Because this is hinged here. Okay, this is hinged here. Both are hinges. Okay. So hinge forces also will be there. So their torque about this one is not 0. So I cannot conserve angular momentum at least about this point. Same way about this point also I cannot conserve angular momentum. Okay, about this point where these two forces are acting, about this point of contact. Then also it's not 0 because it's this hinge and this hinge are there, hinge forces are there. So angular momentum I cannot conserve. Right? Then what to do? Now we'll talk about angular impulse. You can think about angular impulse in this case. Right? So what we can say about angular impulse? We'll talk about individually. It's angular impulse on this one and angular impulse on this one. On this one angular impulse, this force is applying. This force is applying, right? It's acting in this direction and it's trying to decrease its speed. So similar to the previous question, I am taking the impulse of this one as negative. So what is the impulse? Radius of this one is r1 into f dt. This is impulse and I am taking this as negative. Or you don't take this negative. So you take negative this one. Take negative. So say that whenever impulse is outside, okay, outside is positive and inside is negative. So minus r1f equal to I, final one is omega 1 minus omega. So initial is omega, final is omega 1. Right? This first part. For this one you see, what is in this case? Now its angular momentum is inside. It's inside. What we have said already, which we are going to take positive, outside we will take positive. Okay? So here in which direction? This force is there and it's trying to rotate it in clockwise direction and impulse is inside. So we'll say negative. So minus R2 F dt equal to I to omega 2. Just check with the sign first if I am doing any mistake. Okay, first is we took this as negative, so I have written negative over here. This is positive. Okay, for this direction This direction is coming inside only, and this is also inside. Okay, so this is here. Now what we can do in this case? Now this R2 I am taking outside. Okay, minus R2. Then we have f dt. This minus minus you cancel this. R2 f dt equal to I2 omega t. So f dt value is what? F dt value is coming I2 omega 2 by R. Now this value I am going to put in this one. This equation is what? Minus R1 into f dt. F dt is this. So I2 omega 2 by R2 equal to I1, not I1 omega minus omega. This is our second equation. This is our second equation. First equation is this. You already have a relation between omega 1 and omega 2. Right? So we can change. This omega 1 I can write in terms of omega 2 and then I can get omega 2 value. Same way we can get omega 1 value also. Right? So this is one of the questions which gives you an idea that how conservation of angular momentum and angular impulse we need to think about. Angular impulse you can apply anywhere wherever this rotation is happening because of the impulse, because of the torque. Even though you cannot conserve angular momentum, but certainly you can still apply the angular impulse concept. Okay? Now similar to impulse question also I can ask. Similar things you can do in angular impulse also. What is that? Okay, here I did not calculate the value. I am leaving it for you. Right? I have given you both the equations. Just put both the equations, you will get the answer. So I am leaving it for you. Right? So okay. One more, just an example I will give you. I have not calculated. Okay. So one more thing is very similar to what we did in the last chapter. If you remember, similar question we did. Suppose this is pulley over here. Here is one block. Okay. And suppose when there is one bullet is coming, and bullet is striking to this, and they are asking us what is its moment of inertia is that. How to do that? If you remember, we did this question in the case of last chapter with the help of conservation of momentum also we did, and with the impulse also we did. So here you see that first what happens here, impulse will apply. So speed is u, we'll find. Okay, what will generate over here? T. T also is here, and this is applying normal contact. Okay, and then T. And who is going to rotate this? T. Impulse of T will rotate this. So we will write T dt into R equal to I omega. And here you will be writing N minus T dt. N dt minus T dt equal to its change in momentum. For this one, N dt equal to change in momentum. But here only, this is only new. All other things we did in the last chapter. What is that? T dt into R equal to I omega. Okay? And one more thing you will be writing, its speed. If this is going with V, then V will be equal to R omega. So you can use the equations over here for this. Right? So this is angular impulse. In our next class, we will be starting combined translation plus rotation. Okay? That will be the last topic of this one. Alright? Okay? So see you then in tomorrow's class. Bye bye.